Okay, thank you so much for the invitation. It's a great pleasure to speak at this seminar. So yes, I would like to talk about Grothendieck classes of quadric hypersurfaces and involution varieties. So, okay, let's start by fixing a base field with OK. And let's use the following notation. So I will write var with OK. So this will stand for the category of algebraic varieties. And by an algebraic variety, I mean a reduced, separated K-scheme of finite type. And let me start with the main definition of the talk, which is this Grothendieck ring of varieties, which I will denote by K0 of var with OK. So just a historical remark, it was introduced in a letter from Grothendieck to Serre. It was in 16th of August of 1964, so a long time ago. And how is this ring defined? It's pretty easy. So in terms of generators, we just take for generators the isomorphism classes of algebraic varieties. And then we impose the following relations. So we impose that whenever we have a closed subscheme, Z inside of X, so closed, the class of X becomes equal to the class of Z, the closed subscheme, plus the class of the open complement, so X, Z. So these are usually called the Caesar relations, because morally speaking, what they say is that if you have your algebraic variety X, and then if you have your Z here, then if you grab a pair of scissors and cut Z from it, the class of X and the class of Z and of its closed complement, open complement, are actually determine each other. So it only matters the pieces that you are using, not the way you are gluing the pieces in this Grothendieck ring. And it's a ring, it's not just a group. And so the multiplication is as you expect. It's defined, so the way you multiply two classes is by taking its product over with OK. So this gives you a ring. Maybe very basic remarks about this ring. Well, the 0 is in fact the class of the empty algebraic variety. The 1 is the class of a point. So of course a point, I mean spec K. And an important class here is what is called L, usually denoted by L, is the class of the affine line. Well, let me give you just let me just make a very quick and simple computation just to give you a flavor of how things work in this Grothendieck ring. A very simple computation is the following. Computations. So it's well known that if you have the projective line, then you can think that the projective line is actually glued from the from A1. Sorry, is glued from the point. Is glued from the point with A1. So consequently, using these Caesar relations, this tells you that the class of the projective line is actually L, the class of A1 plus 1, the class of a point. And then in the same spirit, projective space, you know that it's glued. You can obtain it by gluing it, previous the Pn minus 1, where you glue the n-dimensional affine space. And so once again, using this Caesar relations, this tells you that the class of the projective space is equal to Ln, then plus the class of Pn minus 1, and then by recursion, so this, again, you know that it's Ln minus 1 plus the class of Pn minus 2. And so you continue at the very end, you conclude that this class is Ln plus Ln minus 1, etc., until L plus 1. So you see that it doesn't matter how things are glued together. What it really matters is the pieces that we are using to do that. Okay, so this ring is quite famous. So this it was defined a long time ago. It's important in several areas, in particular in motivic integration. But one should say that this ring is very complicated. And it's actually very mysterious. There are a lot of things that happens on this ring, and we don't have much control about it. So it's still nowadays purely poorly understood. So different authors study this ring using different techniques and try to answer different questions. Today, I'm going to focus on just one very simple implication, which is the following. So the implication is the following. Suppose that we have two algebraic varieties that have the same Grothendieck class. Does that imply that they actually are isomorphic to each other? And so you see this implication and you immediately say, well, this is quite stupid. Of course, it doesn't work. Of course, it's false in general. So let's see some examples of why this thing does not work. So one very simple example would be, one example here. So suppose that you have the affine line. So you take for x the affine line. So you can just think of it doing this. And then you take for y this ordinary cusp, so defined by spec of, so you take two variables, and then you impose this relation x cubed minus x squared. So, and you can draw it something like this. So these two algebraic varieties are not isomorphic. One is smooth, the other is not even smooth. But what happens here, it's actually that they, although they are different, they are, although they are not isomorphic, they are piecewise isomorphic. So somehow these two pieces here, so the yellow piece and the green piece, are the same. And since they are the same, and since it doesn't matter how the pieces are glued together, it only matters what the pieces are, these two non-isomorphic varieties will actually have the same Grothendieck class, although they are not isomorphic. So clearly the implication that I was considering is false, and you see this very simple example why it is false. And so you can also ask, maybe this is the general phenomenon. Maybe what's happening is that if the two algebraic varieties have the same Grothendieck class, it's actually because they are piecewise isomorphic. So one may wonder if this is the only reason why we have identification. So these two things are piecewise isomorphic. Well, it turns out that that's not only the case. So there are examples of algebraic varieties which are not piecewise isomorphic. Of course, if two algebraic varieties are piecewise isomorphic, they will have the same Grothendieck class. But there are examples, let me give one. An example, this is due to Borisov, it's in characteristic theory, of two algebraic varieties which are not piecewise isomorphic, but nevertheless they have the same Grothendieck class. So this emphasizes that there are a lot of identifications in this Grothendieck ring. So let me just mention this. So suppose that you have a vector space of K of dimension 7, and you choose a subspace. So here you take the second exterior power of the dual of V, and you take a subspace, a linear subspace of dimension 7 once again, and you make a generic choice. And then, so you can think about an element in this W, so that corresponds to a skew-symmetric bilinear form, which we denote like this, on V. And so given this generic choice of this linear subspace, we can build two algebraic varieties, the X. So this is defined, so this will sit inside of the Grassmannian of planes on V. And we will consider those planes inside V with the property that when you look at this skew-symmetric bilinear form, and you restrict it to P, it vanishes, and you want this to vanish for all elements that are in capital W. So you define in this way a closed subvariate inside of the Grassmannian, and also out of this data you can consider Y. Y is defined as those elements that are in W, such that its rank, so this skew-symmetric bilinear forms whose rank is actually strictly less than 6, and this sits inside of the projectivization of W. And it turns out that for a generic choice of W, this X and Y, they are in fact smooth Calabi-Yau threefolds, and they have this property that the Grothendieck classes, they are not the same, they don't have the same Grothendieck class, but they only have the same Grothendieck class after multiplying by L6, so multiplying by the affine line. So in other words, concretely, that means that when you cross with A6, then these two algebraic varieties have actually the same Grothendieck class, but interestingly, so these two things, they are not piecewise isomorphic. So this tells you that in fact there are a lot of identifications occurring in the Grothendieck ring of varieties, and so morally speaking, it tells you that this implication is false, and it's extremely false. Let's say it like this. So the point of today's talk is actually to say that this implication is also true in many cases. So this is the goal of today's talk, is to actually explain some cases where this implication actually holds. So you have some kind of rigidity saying that when you look at the Grothendieck classes of your varieties, they are the same if and only if they are already isomorphic. So you cannot have strange identifications in the Grothendieck ring. Okay, so let me state the results in this direction, which are as follows. So statement of results. And I will start by talking about quadric hypersurfaces. And so the results are as follows. So we are in characteristic 0. And suppose that I have a non-degenerate quadratic form. And then one can associate to it several things, of course, several invariants. So one can look at its dimension, which is a dimension of V. One can look at its discriminant. So this is an element of the invertible elements modulo the square classes. So this is well defined in the case where the degree of the dimension of K is even. So maybe let me just recall this because one possible way to define it is that you look at this the associated bilinear form associated to your quadratic form, which you define it like this: b plus w minus qv minus qw over 2, and then you study the determinant of this bilinear form. So this doesn't make much sense in this sample. You need to choose a basis. So when you change basis, this number changes, but actually it's well defined when mod out by the square classes. So you have this well-defined number, and then you introduce a sign. So this discriminant is also usually called this sign determinant, and you extract this element. So this is an invariant of your quadratic form. And then another thing that you can extract is the even Clifford algebra. So the even Clifford algebra. So let me recall that what you do is the following. So you start with the tensor algebra on V, and then you can mod out by this ideal generated by this element. So if you stop here, you get the exterior algebra. So what you can do is actually to quantize the exterior algebra in the sense that you perturb it by introducing here the values of your quadratic form, and this for every element of V. So when you do this, you get an algebra which is actually not n-graded. It's because this element has degree 2 and this degree 0, but it's nevertheless Z2 graded. So if it's Z2 graded, you can actually extract this degree 0 part, and that's the even Clifford algebra. And then, of course, you can consider the quadratic form, the quadric hypersurface inside of your projective space. So this quadric hypersurface. Okay, so what can we say about quadric hypersurfaces? So it's the following result. Let me call it theorem 1, which says the following is: suppose that you have two quadratic forms such that the associated quadric hypersurfaces have the same Grothendieck class. So suppose that we are in this situation, then it turns out that the even Clifford algebra are actually isomorphic. So this is telling you that if you are working with quadric hypersurfaces, the even Clifford algebra, it's actually an invariant of your Grothendieck ring of varieties. So somehow the even Clifford algebra is preserved under these Caesar relations. And let's say an application of this, since the even Clifford algebra contains quite a lot of information, one application is the following. So suppose that you have two quadric hypersurfaces with the same Grothendieck class, then that implies that, well, if you are in low dimension, so if you are when the dimension of Q is less or equal than 4, so let me mention that if two algebraic varieties have the same Grothendieck class, they have the same dimension. So the dimension is also an invariant of the Grothendieck ring. So this condition here on dimension of Q is actually equivalent to the same condition on Q prime. So that's what I'm not trying to do on Q prime. So this implies that they are actually isomorphic to each other. Another possibility is that, so this is in low dimensions for any field, but if you restrict for those fields where the third power of the fundamental ideal vanishes, then in this case, you have this isomorphism independently of the dimensions. So let me just maybe rephrase this application in a more concrete way. So this, the low dimensional case is basically telling you that when you take quadric hypersurfaces, and you take them, you restrict yourself for dimension less or equal than 2, and you consider them up to isomorphism, then this actually embeds inside the Grothendieck ring of varieties. So there are no further identifications that can occur that are not the notion of isomorphism. So in particular, you cannot have non-isomorphic quadric hypersurfaces which are piecewise isomorphic. So for example, maybe a simple example, let's say over the rationals, you can see, for example, this family here, this family of quadric hypersurfaces here inside of sitting inside of P3. They are actually this family, which is parameterized by those prime numbers which are congruent to 3 mod 4. So this is actually an infinite family. It's an infinite family. There are an infinite number of primes which are congruent to 3 mod 4. An infinite family of non-isomorphic surfaces whose Grothendieck classes remain all distinct. So this is a particular case. And the other situation is when we are working with fields where the third power of the fundamental ideal is 0, it vanishes, then it actually works for all quadrics. So we take all quadric hypersurfaces and we consider them up to isomorphism, then this actually embeds in the Grothendieck ring of varieties. So there are no further identifications among those algebraic varieties. So maybe let me recall this condition on the field being 0. Well, there are many examples. You can have fields of transcendent degree less than or equal than 2 over an algebraically closed field. You can have p-adic fields. You can have also totally imaginary number fields, etc. Let me now make a remark about these two conditions. So one is for low dimensions, and the other is for any field. So one may wonder if there is a relation. Well, in these particular examples of fields that I've given of whose third power of the fundamental ideal vanishes, in this case, any quadric of dimension greater or equal than 5 is actually isotropic. And so one may wonder that maybe it's just a matter of working with quadrics of dimension up to 4, but that's a remark, as you in the audience probably all of you know. Given any integer n, we have these results of Merkuriev saying that actually there exist fields for which there are quadrics. So the quadratic forms there such that this condition is satisfied by the field, and the dimension of your quadric is 2n, and the quadric is anisotropic. So so we have many examples of quadric hypersurfaces where actually you have this phenomena where they remain distinct in the Grothendieck. Okay, so now let me generalize these results. So going from quadrics, we can go one step further. So we can have another statement of results. And now about involution varieties. So here again, we are in characteristic 0. And now the starting data, it's a central simple algebra, the central simple K algebra. and an evolution of orthogonal type. Evolution of orthogonal type. And then, as you know, we can attach to this several invariants. We can look at the degree of our central simple algebra. We can look at the discriminant of this central simple algebra with an evolution of orthogonal type. So again, it's well defined if we mod out by the group of squares, and this well defined in the case where the degree is even. We can also define an even Clifford algebra, and also we can associate with an evolution variety. So this is an evolution variety. Let me say some words about this variety. So concretely, you can think of it as so you can look at the you can look at ideals. You can look at ideals of dimension the degree of A. You can look at right ideals. I inside of A, which are of dimension degree of A. And so if you stop here, you have this definition. So inside of the Grassmannian of A, and you take things of degree A. So if you stop here, you just have the classical Sevre-Bell variety, but then you impose this extra condition that when you take the evolution of I, you get 0. So you get this closed subvariety inside of the Grassmannian. So you have this explicit definition, but a more conceptual viewpoint, which is similar to Sevre-Bell varieties, is that you have this bijection between central simple K algebras with involutions of orthogonal type. So let me write it like this. And let's say that they have degree E, and we consider them up to isomorphism. Then we have this one-to-one bijection with, on the other side, we can look at those smooth projective K varieties. X of dimension degree of D minus 2, such that when you base change to the algebraic closure of K, you get actually the unique possible quadric that you have over there, which is X squared D minus 1 equals 0, and this sits inside P D minus 1 of K bar. And then you consider all those up to isomorphs. So it's really similar to Sevre-Bell varieties. It's actually a closed subvariety of the Sevre-Bell variety of A. And the correspondence is, of course, given if you have this, you assign to it its involution variety. So here you have two viewpoints on involution varieties, the more explicit one and the more conceptual one. So let me give you some examples. So if A, the central simple algebra is split, well, in this case, this implies that involution is actually the adjoint involution, of a quadratic form. Okay, and so this implies that in this particular case, the evolution variety is nothing but the quadratic hypersurfaces associated with this quadratic form. So in this sense, we are generalizing what we have done previously. Also, another important remark is that if you are in this situation with the degree of A being odd then in this case is because A is split. So in other words, when the degree of A is odd, you don't have interesting central circle algebras with involutions of orthogonal type. So we are just in the setting of quadratic forms. And then another example is the following. So another example is that when you take the degree of A to be 4, and you take, moreover, you impose that the discriminant be trivial in the sense that it's a square class, then it turns out that this is actually isomorphic to A1 star 1 tensor A2 star 2, where these two things are actually quaternion algebras, and equipped with the canonical involutions, which are these symplectic involutions. And this implies, so this as explained in this pioneering work of Tau on involution varieties, that in fact the involution variety, in this case, it's actually the product of the quadric associated to this quaternion algebra times the quadric associated with this quaternion algebra. So in other words, under this, in this particular case of degree 4 and trivial discriminant, the involution varieties are the products of quadrics, products of two quadrics. Okay, so given all this, what happens is that the previous results actually generalize. And so we have a theorem 2 that says the following, that once again, if you have two involution varieties that have the same Grothendieck class, then their even Clifford algebras are actually isomorphic. And in the same spirit, since even Clifford algebra contains a lot of information, implication number 2 is, as before, is that if they have the same Grothendieck class, then well, when they become isomorphic, and they are actually isomorphic, and this in all dimensions, and the degree of A is less or equal than 4. So once again, here, if they have the same Grothendieck classes, the degree of A and A prime will be the same because they correspond to the dimensions. And also, you have this in arbitrary dimensions. They are isomorphic as long as we're working with fields where the third power of the fundamental idea is matched. So these theorems to theorem 2 and application 2, remark. So this theorem 2 and this application 2, they greatly generalize our previous theorem 1 and our previous application 1. So this theorem 1 and application 1 correspond precisely to the cases where A and A prime are split. So this is some kind of the twisted form of theorems 1 and application 1. And one thing that one should mention here, emphasize, is that theorem, the way I stated, is false. So in fact, let me mention this. So this theorem 2 and this application 2, they actually require an assumption. Let me make this very precise. And the assumption is the following: is that I need to assume that A and A prime are split precisely in this situation, precisely when the degree of A is 4 and the discriminant is trivial. So precisely in this case. So let me just mention once again that I'm stating this condition on this rectangle using just A, but I could use A prime because if the involution varieties have the same Grothendieck class, the degree does not change, and also the discriminant does not change. So this is equivalent with A prime and star prime. And another way to phrase the assumption is that is actually to say that, well, the involution varieties that I'm considering in this particular case are actually just the product of the same conic. It's product of the conic by itself, where A1 and here the involution A star is the conic of A1 prime plus the conic of prime, where A1 and 1 prime are coterminal. So I'm saying that this theorem and the theorem 2 and application 2, in this case of degree 4 and trivial discriminant, I need to restrict myself to quadrics. So I'm still generalizing to theorem 1 and application 1, but in this particular case, this theorem and this application are actually false. And let's see why. Well, because in this particular case, things have been previously studied, and the relation that we encounter in the Grothendieck ring of varieties, here I'm saying that it's the isomorphism relation. They are isomorphic if and only if they have the same Grothendieck class. And I'm saying that in this particular case of degree 4 and trivial discriminant, the relation is not the relation of isomorphism. And this is something that was previously understood. It's the theorem of Kolar. So if you have A1, if you have 4 quaternion algebras, so suppose that you have 4 quaternion algebras, then the following are equivalent. The following are equivalent. So first of all, this product of these two conics have the same Grothendieck class as the product of these two conics. That is actually equivalent, not for them to be isomorphic, so this is where it fails, but for them to be birational to each other. And also a more algebraic characterization of this equality of Grothendieck classes is that actually if you look at A1 and you look at its Brouwer classes, and you look at the subgroup of the Brouwer group generated by these two Brouwer classes, they actually generate the same Brouwer group. That's actually equivalent. So this is happening inside of the Brouwer group of your system. So you see that, in fact, in this particular case, the theorem is false, and the good relation, the good notion, one should replace this isomorphism by irrationality. And you see that it actually fails with isomorphism because we can take the following example. So you take, you simply choose a non-split quaternion algebra. And then you can look at, you take the associated conic and you cross with P1, and that turns out to have the same Grothendieck class of the conic cross itself. So this is clear, for example, from this third condition. You see that these Brouwer classes generate the same subgroup. It's actually the subgroup generated by A. So they have actually the same Grothendieck class, but nevertheless, these two products are not isomorphic to each other. So this way we have actually a complete picture of what is going on. The equality on the Grothendieck classes corresponds to isomorphism, except in this particular case where it corresponds to irrationality.
Okay, so I have a question. What about the case of cerebral varieties?
Of cerebral varieties, yes.
Yes.
In that case, you can say something, but I cannot have a result as powerful because what you can say, I mean, you cannot recover the cerebral variety. The only thing you can say is that if they have the same Grothendieck class, somehow. Yeah, let me explain that a little bit later, because I'm going to try to sketch a little bit the proof of how these things work, and then it will be simpler for me to explain what's happening with cerebral varieties, if you allow me.
Okay, we keep that for the end, right? Okay, thank you.
But I can tell you right away that no, you cannot the equality on the Brouwer classes does not give you an isomorphism on cerebral varieties. It gives you. You can show that they are birational if you assume that the degrees of the central simple algebra that you are using are low enough. I think up to 6. Then you can. That implies that they are birational to each other.
Okay, no. Yeah. So this is related with Smith-Source conjecture, right?
Yeah, exactly.
Yeah. Yeah. So that's interesting. I mean, I think.
Yeah. So this is well, this is what I wanted to say, and now let me try to give you a very brief sketch of proof. Let's say like this, because all of this is commutative somehow. We are working with algebraic varieties, and I'm actually, in order to prove these results, I'm using some kind of non-commutative techniques. So let me just say something like this. So sketch of proof. Of theorem 1. So let me just focus on theorem 1. As you expect, theorem 2 will be a generalization, so it will be conceptually the same idea, but a little bit more complicated. So the first ingredient is that there is actually a motivic measure, so which I call a non-commutative. This NC stands for non-commutative. So there is a ring homomorphism from here to a ring, and this ring is in the same way that you can talk about Chow motives over this space field with integer coefficients. There is a category which is called the category of non-commutative Chow motives. So here you don't work with algebraic varieties, you work, to simplify, you work with differential graded algebras. Okay, and then it's a category, well, it's a symmetric whenever category, etc. You can consider its Grothendieck ring also. So, and it turns out that there is a motivic measure, so a ring homomorphism, that sends a smooth projective variety. So in the case of smooth projective, what you can do is you look at the perfect complexes on X. So you need a little bit more of structure. You need it to be a DG category, so a DG category of perfect complexes. So it turns out that this thing actually carries a generator, so it's actually equivalent to the DG algebra of endomorphisms of that generator. So this object is actually affine in the sense that it's given just by an algebra, but a non-commutative one and a DG one. You can think about it like this, and then you take the non-commutative motive associated to this guy. So it's pretty similar, or conceptually pretty similar, if you are familiar with this, with the motivic measure of Gillet-Soulet, where they do the same, but they go to Chow motives. So here you can actually go to non-commutative Chow motives. And then what you do is the following. So suppose that you have two quadric hypersurfaces that have the same Grothendieck class. So that implies that they have the same motivic measure. Yes, because I have the motivic measure. But this is saying that, it's just saying that by definition of the motivic measure is saying that this non-commutative motive of this quadric hypersurface, this Grothendieck class is equal to the Grothendieck class of this one. Okay, and by definition of having the same Grothendieck class, so this is just a symmetric monadal category. So having the same Grothendieck class, that means that there exists an object, so a non-commutative motive, such that when you add this one, so when you add this one, you actually get an isomorphism. So they are not actually isomorphic, but they are isomorphic up to adding a certain object. So this is classic. And then it turns out that one knows how to compute this non-commutative motive of these quadrics. They are actually given by a bunch of copies of the base field. So as many as the dimension of k minus 2. And then it's here where it appears the even Clifford algebra. So you see that you don't have this motivic decomposition in Chow motives, because here you have this even Clifford algebra, a truly non-commutative object. And then on the same story on the other side, so here you have a bunch of copies of k. So here dimension of k prime minus 2, and then also the Clifford algebra, even Clifford algebra. And then what's happening here, of course, because they have the same Grothendieck class, they will have the same dimension. So in particular, dimension of the quadrics will be the same. So you see that you have the same information on both sides. And so what's happening here is that you can actually cancel this information. So you have this cancellation result that tells you that if you have this equivalence, then that implies that you have actually an isomorphism of non-commutative motives. And then if you have an isomorphism of non-commutative motives, you can actually prove that that implies that these algebras are actually isomorphic. So this is the way, so the ingredients actually are this motivic measure, and then this computation of the non-commutative motive of the quadric hypersurface, and then of course this cancellation here, this cancellation result that allows you to cancel and conclude that you actually have the same non-commutative motives of the even Clifford algebras. So this is a brief idea of the ingredients that are used in the proof for theorem 1, and for application 1, as you probably figured out already. In this application 1, what's happening is that, well, the even Clifford algebra, if you are going up to dimension 4, it actually classifies the quadratic forms. And if you are in this situation where the third power of the fundamental ideal vanishes, again, even Clifford algebra is enough to characterize the quadratic form. So you can actually extract the quadratic. So you are not actually losing any information about the quadratic form. Yeah. So this is what I wanted to say. I mean, I think I still have some time, but yeah, I think I prefer to stop here and maybe answer questions that keep on going. So thank you for your time.
Thank you. Questions, comments?
Yeah, I do have a question.
Yes, please, Corey.
So how is it related to K motives? Is it related to K theoretic motives?
Yes, the precise relation here is
like this computation of K theory of twisted
yes,
varieties.
there exists something in the literature called K motives, which were, if I remember correctly, they were introduced by Manin in this original paper of motives, which is let me just, a possible notation is something like this, K0 Chow. So it's basically there, what's happening is that you do the same story as Chow motives, but instead of working with correspondence, you work with K0. So you see that if you are working with rational coefficients, that's the same thing using Riemann-Roch as working with all the correspondences of arbitrary codimensions simultaneously. So, but if you use this category, that's not enough, because here you don't, the objects still are just smooth projective varieties and then direct factors of it. So you don't have here, for example, that's not good enough to have this motivic decomposition where the even Clifford algebra appears. But then this was, let's say, Manin here in the 60s. And then there is a more general category where this is included, which is, I don't remember the notation they use, that I'm just making it up. So let me call it something like this, where they basically, so this was done by Merkuriev and Panin. And what they did is that they start with smooth projective varieties, but then they add separable algebras to them. And then again, the Holmes between all this is just given by K0. And that category is good enough for these results. And these results are actually happening in this category, which sits inside non-commutative Chow motifs. So everything is happening in this second one, but not in the, everything is happening here, but not in here. Yeah, not in here.
Okay.
Yeah.
Yeah, thanks.
But then you need to, for example, for this cancellation here, you need to have a very good control of how to describe the Holmes between these objects, etc.
Okay.
Okay. Other questions?
So in the exceptional case that's described by Kalar, when the class in K0 is the same, but those two varieties are not isomorphic, are they locally isomorphic?
I mean, they are, I think, if I understand correctly, it gives you a complete, it tells you that they are exactly birational to each other. I think then you can play around with all possible examples. And I mean, I'm not sure I completely understood. All these conditions are equivalent. So the notion of equality on the K0, he was able to say, to describe it as saying that notion for this particular case, it's exactly the notion of birationality. It's exactly the notion of birational. They have the same Grothendieck class if and only if they are birational to each other. Or if you want algebraically, if and only if the Brauer clusters generate the same subgroup. And of course, yeah, the result of Kolar is more general because it's actually for products of quadrics. It works for products of quadrics. Sorry, it works for products of conics. Sorry, and here I'm just working with involution varieties, which in this particular case are products of two quadrics. Sorry. And it's even more general, the result of Kolar. I think it works over a base which is not even a field, etc.
Okay. So another question? Okay, so thanks again for your talk, Gonzalo.
Thank you.
Thank you. We can clap.